Welcome Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. And in this lecture we're going to discuss what to do if we have a rigid body with two different points of interest and we want to know the moment at both points. And we have a whole bunch of forces acting on this body and maybe a couple of couples. Remember those things that add pure moment with no different force. Okay, so we're going to use vector algebra to prove something super handy about how to compare the moment due to applied forces and couples at a couple of different points in a body without necessarily having to go back and recalculate moment due to all the forces using radii from all the lines of force for each of the two different points. And so we're going to use vector algebra to prove what it would take to show what the difference is in the moment about one point on a body and another due to the same collection of forces and couples. Okay, so we're going to start with a rigid body, which of course we have to have for statics, no deformation allowed. And there's a couple of points of interest on it. We'll call it point P and point Q. Don't know why they're interesting. Maybe it's the end of a shaft in the middle. We're going to calculate strength due to different forces. It could be anything, but there's two different points. And we've got a bunch of different forces. So we're going to use summation notation to represent the sum of a bunch of different things. So we're going to use the subscript I to note which force or couple we're talking about. So F sub I summed over I going from 1 to 5 would mean F1 plus F2 plus F3, etc. So that's what that notation is. So we have I different forces. Each of these forces is going to have a point somewhere on its line of action. And that is important if we're going to calculate moment, because we're going to, we'll be looking at radius vectors from our points of interest P and Q to this point A sub I on the line of action of F sub I. And there's going to be a whole lot of I's. So a whole lot of forces on this body. Okay, and we have a bunch of couples, and so we'll use a different indexing letter for couples. We'll use J. So we've got couple 1, couple 2, couple 3, so that's C for couple sub J. So here's a little schematic of this rigid body. It's kind of, we got a blob here to indicate it's a rigid body. We don't know what it's shaped like. As a note, the double-headed arrow indicates a couple or a pure moment, and so it's the direction of that moment. So you can imagine that this one would cause the rigid body to spin on an axis about where that that double-headed arrow is. So we've got a C sub J here. We had couple number 1 over here. An axis line with a little rotational arrow around it is another way of showing moment or a couple. So pure moment, no force. So we've got this symbol, and this symbol means the same thing. So you have couple 1, maybe 2, 3, 4, and ending up at J. And we have many forces. So F1 with a point on its line of action A1, maybe we've got an F2 with an A2, F3 with an A3, and so our general note for that is F sub I with an A sub I on its line of action. Okay, so here's our point of interest 1, P, and our point of interest 2, Q. And of course, we can draw a radius vector between P and Q. And we can draw a radius vector from point Q to any A on the line of action of any force. We're just showing one, but there's a whole bunch. There's a line radius from Q to every A associated with every force. And the same with point P. If we want to calculate the moment due to every one of these applied forces, we'll have to have a radius vector to each of these A's. Point A's, A sub 1, A sub 2, on the line of action of F sub 1, F sub 2, all the way up through F sub I. So we can use summation to add up the effect of all of those forces and moments. So we can say that the sum of the forces acting on the rigid body is given by the sum, and there's our summation symbol, of F sub I, where I goes from 1 to some number n, and that's assuming that there are n total forces. Could be 2, could be 3, could be 500. We don't know. But we can sum them all up. We know that. So we can write an expression for the sum of the moments about point P. And there's two groups. There's the moments that are due to the applied forces, and then there's the couples. And notice there's no radius for couples. Doesn't matter where they are. We proved that in one of our discussions, that couples were independent of position in the moment that they applied to a rigid body. So the sum of the moments about point P is all of the couples plus the sum of, and we'll write our familiar cross product expression for the radius from point P to any point A on the line of force I crossed into the vector expression for force I. And we'll just add that up. This is one moment due to one force, and they're crossed into its radius. And we'll just sum it over all the forces with all of their associated point A's. So sum from for I from 1 to n of R from P to A sub I cross F sub I. So this is the moments from all of the forces. Here's the moments from all the couple. That's all the moments about point P. We can do the same thing with point Q. So the only difference here is the radius is different, right? So we've got the radius vector from point Q to some point on the line of force of all these forces. Same points, but we're starting at a different point of interest to look at the moment about. Same points on the lines of force though. Okay, so here's our two expressions. So wow, this, if you had like 20 lines of force, you'd have to evaluate these radii to all these points of points on the lines of action of the force. You'd have to evaluate all these cross products like 20 times. And then if all of a sudden you said, oh darn, I wanted it about a different point, oh, you'd have to go through all that again. Maybe there's an easier way. So let's see if there is. Let's look at the relationship between the radius vector from point P to all these different points on all these different lines of forces, and let's compare it to this R Q sub A I, because that's really the only thing different about these two expressions is those radii from the points of interest to the points on the lines of forces. Maybe if we found a relationship between those, we could find a shortcut. Well, let's look at the vector addition, see if we can get a relationship there. So we could say, we could show that the radius vector from point Q to any point on any line of force, that's point A sub I for force F sub I, okay, we can say that that is equal to RQP plus RPA. Just good old vector addition right there. Okay. Well, let's just substitute that in for RQA, just like we have in the past when we were doing proofs for couples. So let's substitute this expression in for RQA in our sum of all of these different moments due to forces about Q. So now we would write the sum of the moments about point Q is the sum from I from 1 to n of RQP plus RPA sub I cross F sub I for all the different i's representing all the different forces and all the different points on their lines of action. And then we add the couples. Well, we can distribute again. We can distribute the cross product over addition, and so we can break this up and write it separately. So we can take this RQP portion and separate it from the RPA sub I. So we're going to do that, and we're going to put the RQP portion over by itself, and we're going to leave the rest. Well, if we take a look at what we've got left, and then we look back up here and go, doggone it, these are the same. So when I do this substitution, distribute the cross product and do a little rearranging, I find that the sum of the moments of all of those forces about Q and all the applied moments, the couples about point Q, is the same as the sum of the moments about point P, plus this extra term. What's in this extra term? So basically, if we could figure out this extra term, we wouldn't have to recalculate all of these moment contributions of all of these forces about point Q. So let's look at calculating this. We've got, this term is telling us we've got the sum from I equals 1 to I equals n of RQP cross F sub I. Okay? So this is saying we got at least only one radius vector, but we've got to look at the cross product of that RQP, the radius vector between the 2 points of interest now, and we're going to have to evaluate the cross product of this radius with all the other forces. Dang, that's still a lot of cross products to take. But maybe we could invoke another principle we've already proven to make our life even easier. It's really kind of hard to calculate lots and lots of cross products. It's pretty cumbersome. But it's pretty easy to add vectors. So what we're looking at in this expression is the sum. We're summing I from 1 to n a bunch of moments, because this cross product here is a moment. It's a radius length crossed into a force. So we can basically take the sum of moments and say it's the moment of a sum. Well, that means we can sum all of these forces and then cross RP into one single resultant force vector. So we can do a bunch of vector addition and basically sum all the forces that were applied to the rigid body regardless of where, sum them all up, add the I hats, components to I hats and K hats to K hats and J hats to J hats in whatever force unit, use the same force unit and get a total resultant force. Then just calculate the cross product of our single radius vector between Q and P into that, and that will be the additional moment that makes the difference between the moment of all of those applied forces given the calculation about point Q versus point P. So we just proved that instead of redoing all of our cross product calculations to get individual moments for applied forces about point Q, all we have to do is use what we already calculated for point P, assuming we had already calculated it, then take the sum of the forces, which we probably needed to get already if we were going to evaluate conditions of equilibrium, and calculate one cross product based on a radius vector between our 2 points of interest Q and P that we cared about. So that is a massive shortcut if we are looking at the moment contribution of applied forces at 2 different points on a body, because that is different. Now, we could prove that if you put P and Q close together, this radius expression would be really, really small, and so this contribution would be small, and maybe we could say the 2 moment expressions for the 2 points would be similar if they were pretty close. We can see that with this radius term here. So the moment about Q, our second point, due to the forces and couples, is the same as the moment about P due to those same forces and couples, plus a term that's dependent on the relative positions of P and Q versus the sum of the applied forces. So there's our big shortcut, and this is sometimes called principle of moments. So it's something that you'll use when you're looking at equations of equilibrium sometimes, or just simply looking at needing to keep something from rotating when you're looking at 2 different points on a body. And again, we used vector addition, we used kind of a general way of summing up forces and moments, distributive property of the cross product, and some algebra. And we probably saved ourselves hours of cross product calculations, so well worth it.